Hello, good morning. Can you see my screen? Is it visible? Hello, is the screen visible?
Yes, sir.
Okay, okay, okay. So in the last class, I was talking about square wave inverter. I did the structure, I did the connection of the devices, and I showed that the main device is IGBT. This is IGBT. Actual IGBT is this. Sorry, this will not work. Okay, so this is since I'm showing it in PDF file, it will not work. So actual device is IGBT and the reverse device is a diode. Okay, let me go to this then. So this is a reverse device is a diode. Now one may ask why the diode is required. This is the voltage source inverter. You understand that the voltage is dictated at the terminal. This is the terminal at which the voltage is dictated. This is a supply. Let us you remember that we had how we had split the supply into two parts, one plus VDC by 2 and another minus VDC by 2, and consider the middle point as the reference. This is the reference. We named it as 0.0. This is plus VDC by 2 and minus VDC by 2. Why this is important is this why this point why this diode is important is you must understand that this is a going to the motor. This current is going to the motor. So voltage source inverter. Similarly, the two other legs are there. It's identical. So you must understand that this current being being an AC supply, the currents can be positive and negative. Already voltage being positive and negative has been ensured because we are taking it with respect to the 0 point. So voltage would be plus VDC by 2 and minus VDC by 2. This terminal. Voltage will be plus VDC by 2 minus VDC by 2. That has been ensured. Okay. Now one has to ensure that since it is given to one AC circuit, that means current can be bidirectional. The current can be bidirectional. Current can be going from this end, from this middle point. We called it R to the motor terminal. This is motor terminal. This is going to the motor. This is going to the motor, right? This can go to this, and also we should have the flexibility in the connection. If the current is negative, it should be also allowed. The current could be negative, positive and negative, both currents have to be allowed. So you see, when the switch Q is on, and then the current is positive, the current flow would be through this path, like this. It is going like this. When Q is on, and you have if the current through the machine is positive, then it is a positive current is flowing through the actual IGBT. Okay, but if the current is negative and the switch Q is on, as such, if you do not put the diode, then there is a problem, because that current has to be continuous, and it's an inductor. Current has to be continuous, but you are not giving any path to it, right? Logically speaking, you have, suppose you have not put diodes here and here as well, any direction. You have not put diodes here and there, and the current is negative, right? The negative current is either intending to flow through, this is called collector and this is called emitter. It is intending to flow through emitter and collector. Okay, the Q bar is off, right? So it is intending, but that is not possible. The device doesn't allow it. The IGBT will not allow it. So it will flow. It is not a MOSFET. MOSFET will allow it. MOSFET is a majority carrier device. Okay, the IGBT is more close to BJT, so it is a minority carrier device. And the minority carrier device doesn't allow the current to flow in the reverse direction. Majority carrier device allows, because there is that is like a channel. That's why the name is drain. That is like a channel, and the channel is open, then current can flow, electrons can flow in either directions. So here it is not possible, but you have to have it. So therefore we put a diode, which when the current direction is reverse, it will allow the path current to be continuous. So that is why it is called a voltage source inverter. Irrespective of the current direction, the voltage at this terminal will be plus VDC by 2 or minus VDC by 2. When Q is on, it is plus VDC by 2. When Q is on, it is plus VDC by 2. Irrespective of the current direction, on Q bar is on, it is minus VDC by 2. So this is the this is the feature, the characteristics of this voltage source inverter, and that's why we require a diode. Okay, you may remember it from earlier teaching also, but I wanted to one more time present it to you, right? So in today's class, we will see, we have seen the switching waveforms in the last class. We'll see that switching waveforms, what kind of harmonic profile they produce. We are using a square wave inverter, and we will see what kind of harmonic profiles they produce and what kind of issues they create in the machine. Because we are not in the square wave inverter, we are not doing multiple switchings within a line cycle, within a period T. So therefore there will be not only will create fundamental, will create other low frequency harmonics as well. So what are the magnitudes and what happens to because of that? So we'll do such analysis now. First waveform is very easy. You remember that the waveform is simply this square waveform. This is the voltage waveform. It is magnitude wise plus VDC by 2 and minus VDC by 2. And this waveform is generated with what we call it VRO, where O is the neutral point. So we can apply, by this time you know that this waveform, the fundamental component will look like this, somewhat like this, Harmonic components will be with respect to this fundamental. So what is it can be divided into Fourier series components, and the harmonic component may be like this, maybe third harmonic, let us draw. So third harmonic is 120 degrees, so one cycle will be completed here, 1/3. Yeah, so maybe third harmonic will be so that will be a third harmonic kind of waveform. Similarly, fifth harmonic, similarly seventh harmonic, all harmonics will be produced. So what are the magnitude from Fourier series coefficient? We know that this has no cosine terms because it has odd waveform, odd symmetry. Our 0 is considered to be here, 0 t by 2 plus t. This is the way we have divided the time. So it has only odd wave symmetry. So therefore only sine wave components are there. So it is only Bn components are there. So Bn will be 4 into VDC by 2 pi n into pi, that will be the formula, into sine n omega t, n omega t. Omega is equal to 1 by omega 2 pi into f is equal to omega. So 2 pi into t. Okay. Sorry, omega is equal to 2 pi into t. So t is equal to omega by 2 pi, right? Right. So so this way you can get the B1 is equal to 4 VDC by 2 by pi sin omega t, that is B1. So this will be writing it as we will call it as VR fundamental component is this. VR fundamental is this. Then Vy1 is nothing but same magnitude 4 dc by 2 pi into sine of omega t minus 120 degree. Vb1 is equal to 4 vdc by 4 vdc by 2, yes, 4 vdc by 2 by pi sine of omega t plus 120 degree, right? So these are the waveforms that we will be getting, the fundamental component of the waveforms. What will be the harmonic component of the waveforms? Let us say third harmonic. Third harmonic means VR3. What will be 4 into VDC by 2 by 3 pi into sine of 3 into omega t minus omega t. That is the first point with this one. Then Vy3 is equal to 4 VDC by 2 3 pi into sine of 3 into omega t minus 120 degree. Vb3 is equal to 4 VDC by 2 3 pi into sine of 3 omega t plus 120 degree, right? So there is a third harmonic component. You can see that there is a third harmonic component, right? And you can see that they are in phase. This 3 omega t minus 120 degree is equivalent to sine of 3 omega t. This is also equivalent to sine of 3 omega t. This is what you expect, because you have seen the third harmonic component, which appears to you as a what is that? Common mode voltage. You have seen that. A third harmonic voltage, you have seen that. When you sketched the common mode voltage, you have actually sketched the third harmonic voltage. Third harmonic and sixth harmonic and ninth harmonic and etc. It looked like a square waveform. If we just independently do the Fourier analysis or Fourier series analysis of that waveform, we'll get third and all multiples of that. Third harmonic, ninth harmonic, then 3 times is it will be all odd numbers, 1, 3, 5. So third, ninth, and then 5 times is 15th harmonic, and so on and so forth, right? So that common mode voltage is representing all the triplet harmonic components, not even numbers but odd numbers. Sixth harmonic is not there, but odd numbers. Odd number of triplet harmonic components will be represented by that. So we expect it. Okay, we expect this kind of thing, that these are all in phase, right? the third harmonic components are all in phase. They are third harmonic component. That's why we call it a common mode voltage. It's a part of the common mode voltage. Actual common mode voltage wave shape is like a square waveform in the case of a square wave inverter. But if we do the Fourier analysis, we get the third harmonic component from that. Okay, so this is this thing. Let us write also the fifth harmonic component now. VR5. So 4 into VDC by 2 is the original one, and to 5 divided by 5 pi sine 5 omega t. Vy5 is equal to 4 by 5 pi VDC by 2 sine of 5 into omega t minus 120 degree, right? 5 into 120 degree. So, and B5 is equal to 4 by 5 pi into VDC by 2 sine of 5 into omega t plus 120 degree. Now I want you to look at this waveform, this number a little bit. What does 5 omega t minus 120 degree imply? So let us see what is 5 omega t, 5 into omega t minus 120 degree imply. It implies that it is sine of 5 omega t minus 600 degree. So what is 600 degree minus 600 degree? So this is 0 degree, this is 120. So 360 degree is this, minus 360 degree is this. So so minus 600 degree will be located at what? 360 minus 360 and another minus 240. So it is minus 120 this. So the fifth harmonic component of the Y phase, this is V corresponding to Vy5. Understand that is not located at 120 degree lagging. It is located at what point? It is located at where? It is located at 120 degree leading. So this waveform is essentially sine of 5 omega t plus 120 degree, right? So you see a change is happening. Change in what? What is happening in this? So it is changing the phase sequence. So Y phase normally our convention of Y phase is that Y phase will lag the R phase by 120 degree, which has happened in case of the fundamental component of the waveform. Our switching strategy was like that. Whatever I am doing to R phase, we are switching Y phase after 120 degree. That was the switching strategy, where we have produced square waveforms, where we have produced discontinuous square waveforms. Now, after Fourier analysis, what we are seeing is that the fundamental component is maintaining that kind of phase shift, meaning that fundamental component of the Y phase is lagging the R phase, and the fundamental component of B phase is lagging the Y phase. There is no doubt about it. But there is interesting thing happening at the fifth harmonic. Third harmonic component, all of them are in phase. There is no phase shift in the third harmonic component. But the fifth harmonic component, among themselves, they are changing the phase sequence. Instead of RYB phase sequence, it is now exhibiting RBY phase sequence. So V5, that waveform is this. So this is sine of 5 into omega t plus 120 degree. So which it essentially means that it will rotate, and then finally it will become equal to sine of 5 omega t minus 120 degree, right? So this way they have become they have interchanged the phase sequence, in this manner, right? So the phase sequence is now B, I will say R5, D5, Y5. You remember that. So let us see then about the seventh harmonic component. What happens to the seventh harmonic component? So VR7, what is happening here? That is 4 VDC by 2 by 7 pi into cos into sine of 7 omega t, the first one. The second one is VY7, that is equal to 4 by 7 pi VDC by 2 into sine of 7 into omega t minus 120 degree, which means that it will be this part is sine of 7 omega t minus 840 degree, which essentially means 720 minus 720 minus 20. So it is producing an angle, phase shift angle of sine of 7 omega t minus 120 degree, right? So seventh harmonic is again returning back to the original phase sequence. So that is what we notice. Right. So seventh harmonic component V So seventh harmonic component V RYB B7 is equal to 4 into VDC by 2 by 7 pi into sine of omega t minus 7 into omega t plus 120 degree, which will become equal to 4 VDC by 2 7 pi into sine of 7 omega t plus 120 degree. So the here seventh harmonic corresponding to seventh harmonic, the phase sequence is still R, Y, B, right? Right. Now what happens when we go to the phase sequence of line to line voltage? So that is what we'll discuss now. So look at the line to line voltage one more time. Here we had sketched the line to line voltage. You remember the line to line voltage. You just see the line to line voltage, right? Where is the line to line voltage? This is the line to line voltage. This one is the line to line voltage. Now you had VRY. Look at VRY. That is the line to line voltage. What do you see? What do you observe? In fact, I have drawn an equivalent sine wave there. So can you observe one thing? Can you see that the DC value, not only the zero, if I want to make this waveform VRY symmetric, odd wave symmetric, then where should my 0 be? My 0 should then be shifted by 30 degree, and not only 30 degree, it would be leading by 30 degree. The 0, if I do the 0 shifting by 30 degree, 0 of the waveform is shifted by 30 degree, then I can again treat them as a symmetric odd waveform. Why I am doing it that I can do Fourier analysis of the waveform with the original 0. Original 0 is assumed to be the 0 of the VRO waveform, 0 of the VRO waveform, that is considered to be original 0. And I can do Fourier analysis of VRY as well based on that. But then the symmetry will be lost, and the symmetry, if it is lost, then we'll have both sine and cosine components. So I have to calculate both AN and BN component, which is cumbersome. So instead of that, I am looking at the waveform and thinking that I retain the odd wave symmetry of this waveform if I just shift my reference, the 0 reference, phase reference, by 30 degree in the leading direction. So you can see that the equivalent sine wave half part I have drawn, and then the integration is happening. Then the waveform is can be interpreted as this, that from 0 degree to 30 degree its value is 0. From 30 degree to 150 degree its value is VDC, and from 150 degree to 180 degree its value is again 0. Then from 180 degree to 210 degree its value is 0. Then from 210 degree to 330 degree its value is minus VDC. Note that it is not minus VDC by 2. Minus VDC by 2 was the level we got when we looked at the phase waveform with respect to the neutral of the inverter. But here we are getting a voltage level of, because it is a line to line voltage VRY, we are getting a voltage level of VDC. Okay, and subsequently from angle 330 degree to angle 360 degree, the value remains to be 0. So this is the shape of the waveform, and we will find out the Fourier component being fully aware that our 0 is now shifted, right? So let us do this now. So we'll do VRY1. So it is nothing but, you remember that we do this thing by an integration. Let me write the formula 2 by T. I am just writing only the component of the BN, what we call it BN. So because it's odd symmetry, 2 by T, 0 to T. This is the basic formula, ST sine of n omega t dt, right? That is the basic formula. So if we look at it, then what we can do is this waveform we will be integrating from what point to what point, right? So fundamental component, if I want to have, so fundamental component will be integrating only between, because 0 is shifted, only between 30 degree to 90 degree. That is the angle will be integrating, because after that it is just identical thing and 4 times that. So we will be doing 4, okay, 4 times that, and omega t is equal to 2 by t, t is equal to 2 pi, because omega I have taken here, omega I have taken here, and this is nothing but sine theta now, sine theta, because ft is equal to 1, and this magnitude is VDC, magnitude is VDC. So after taking out VDC, ft has become equal to 1, because the label is that. After taking out omega t, I have got n is equal to 1 in this case for fundamental component, n is equal to 1. So sine theta d theta we are integrating. We are integrating from 30 degree to 90 degree, because 0 degree to 30 degree this value is 0, and after that 4 identical time intervals come and 4 integration happens. similar for number 4, so the multiplying factor 4 is coming here. So and so this is the basic thing. So what is that value? So this value is, this 2 cancels, so 4 VDC by pi, and this thing is minus cos theta, so minus cos theta, which we have to do from 30 degree to 90 degree, which is nothing but minus minus 4, first I write 4 VDC by 2, and minus sine 90 degree plus minus cos 90 degree plus cos this thing, so it is nothing but is equal to root 3 by 2. So 4 VDC by 2, 4 VDC by 2, sorry, 4 VDC by pi into root 3 by 2. That is the magnitude, that is the component, right? 4 by 2 into root 3 by 2, right? So you can see the observation, you can do a comparison of that. So what was the fundamental in the previous case? R phase fundamental. R phase fundamental was how much? Let me see. This is the R phase fundamental. What I am saying, the R phase fundamental is this 4 VDC by 2 pi. That is the fundamental. And why? What is the fundamental now in the line to line? 4 VDC by 2 pi remains. Along with that, a factor comes is root 3. Is it surprising? It is not surprising, right? We all learned that line to line voltage is root 3 fundamental component. If this is happening in case of a fundamental component, but when there is no harmonics are not considered, you know the line to line voltage magnitude becomes root 3. So this is not at all a surprising result. It is just root 3 times this magnitude. But what is this? What is the shape of the waveform? The shape we will be writing it as, this is the magnitude of it. So shape will be writing as complete expression of the fundamental component of the line to line voltage. We will be writing it as 4 VDC by pi by 2 pi into root 3 into sine of, tell me what should I write? Omega t plus 30 degree, right? Because I am cleverly adjusted the zero shift to make my integration simpler. I have adjusted the zero shift. So this would be the fundamental component. Agreed? Do you agree? Right. So next is that then the Y phase. Y phase will be how much? 4 VDC by 2 pi into root 3 into sine of omega t plus 30 degree minus 120 degree. That is the sequence. Phase sequence wise, it is minus 120 degree. Then y1, this is y1, right? So VRYB, VB1. What is VB1? 4 VDC by 2 pi root 3 into sine of omega t plus 30 degree minus 100 plus 120 degree, right? So this would be the thing. If a phase sequence wise, if I want to draw it, so if it was the original 0 is here, if the original
second one should not be VY1, it should be YR.
Oh, sorry, thank you. And B now B RY
YB, sir, YB.
YB and V B R. Thank you. Yeah. RY1. Yes. 1. Right. So if we draw the phase sequence of it, so how do I show it? If this is the original 0 degree, so RY is coming 30 degree here. Okay, this is VRY1 and the other one is coming minus 90 degree, so it is here. this is V y b1, and the other this thing is becoming, this is VBR1, VBR1, right? So this is the way these three things, but phase sequence is still RYB because this is minus 120 degree. This is another minus 120 degree. So this is phase sequence is still RYB in the line to line as well, fundamental, as far as the fundamental is concerned. Okay, so now let us see the third harmonic of it. Third harmonic was there, but here will there be a third harmonic? Let us see. We write the third harmonic. So in the third harmonic, we directly go to this part. We don't whatever may be the magnitude, we don't, for the timing we will ignoring it. Just trying to see what will be the sinusoidal component of it. So sinusoidal component would be 3 into omega t, 3 into omega t, okay, I will not draw that. 3 into omega t plus 30 degree. Okay, another will be sine of 3 into omega t minus 90 degree. Another thing would be 3 of sine of 3 into omega t plus this was how much? This is 150 degree. 3 into omega plus 150 degree. 150 degree. Okay, so you can see that this is 90 degree and this is plus 90 degree. That means this is happening here. The third harmonic is coming how much? This y phase, this is corresponding to VRY3. This is corresponding to VYB3. This is corresponding to VBR3, right? So that is minus 90 degree, minus 90. It is also in the same phase. This is same phase. Okay. Then what about 450 degree? That is also equal to plus this thing plus 450 degree. That is also in phase. So you can see that they will be in phase. As such, their waveforms are indicating that they are all in phase. That is what we expect also, right? We expect also. But what is the magnitude? If you do the magnitude here, then you have to integrate. I'm not writing first coefficients again and again. First coefficients also is easy to write, but I'm not writing it. First coefficients would be 2 by 2 pi into 4 by, since it is a third harmonic, so you will put a 3 pi, and integration you will do between 30 degree to 90 degree of this one sine 3 omega t, which would be equal to d omega t d theta 3 theta d theta, so which will be equal to 0, right? Which will be equal to 0. So the third harmonic component will not be present in this thing, in the waveform. In the waveform, the third harmonic component is not there, which is also from our common sense we can find that the third harmonic component is absent in this. The fifth harmonic component, if you look at it, what is the fifth harmonic component? Fifth harmonic component, so that is VRY5. Okay, you have to integrate what? You have to integrate from you have to integrate it, and you will get now let me write it. What is the integration? 2 by t, 2 by 2 pi. So 4 into integration, what you are doing is sine 5 theta d of 5 theta, where theta is varying between 30 degree to 90 degree, right? Theta is varying from 30 degree to 90 degree. So this value is again becoming equal to minus root 3 by 2. Okay. Seventh harmonic component, similarly VRY7, this also if we integrate, we will get a number minus root 3 by 2. So what we are seeing is that the waveform that we are getting is VRY5, we have to write it as VRY5, we have to write it as, since the magnitude is minus root 3 by 2, you just look at it very carefully, minus root 3 by 2 into VDC 4 by 5 pi sine of 5 into omega t plus 30 degree, right? Which is, and the next VYB5 RYYB5 will be minus root 3 by 2 VDC 4 by 5 pi into sine of 5 into omega t plus 30 degree minus 120 degree, right? And the VY VR5 is equal to minus root 3 by 2 VDC 4 by 5 pi into sine of 5 into omega t plus 30 plus 120 degree, right? So if you see these things, it also shows that the phase sequence is, if you break it in this way, it will show that the phase sequences are changed. The phase sequence of this is now A, R, Y, and B. That is the phase sequence you will get in this case. Because if you look at just to break one of them, let us see that 5 into, anyway, I have already done it. 5 into, this is 5 into 90 degree, 5 into minus 90 degree, 5 into minus 90 degree means 4, it will come down, right? And then reverse, then it is positive. You just see the first one. First one, what is it saying? It is saying that 5 into, the angle is 5 into minus 90 degree. So 5 into minus 90 degree means it is 0 degree, 1, 2, 3, 4, 5 is here. So it is coming here. But you see a negative sign here. So negative sign means it is going up. So therefore, VYB5 is located here. VYB5 is located here, as we had seen earlier. As we had seen earlier by direct integration, we had seen that. Okay. What is that? What is that? RYYB. Okay. This is 1. Sorry. 7. Why is that? No, third. 7. I didn't come. It didn't come. Sorry. So here only I am proving it. I'm sorry. So here I am proving that this would be in is 90 degrees shifted with respect to this one. This is VRY5. Okay, this is sorry, it is Let me draw it properly. VRY5, where is it located? It is 5 into 30, that is 150 degree. This is our 0 degree. 150 degrees here, 5 into this, and with a negative sign. With the negative sign means this would have been 150 degree. With the negative sign, it goes here, right? So this is VRY5. Okay. Now the second one is 5 into minus 90 degree. So 5 into minus 90 degree is here, but with a negative sign. So it goes into 150. Minus 90 degree. 1, 2, 3, 4, 5. What is I'm missing? 5 into 30 is 150. 150 reverse is there. Okay. 5 oh, sorry. This is plus 150 degree. Yeah, it is plus 150 degrees here, and then reverse. Reverse is here. Sorry, not this one. I'm sorry. This is 5 into 30 degree. 5 into 30 degree is plus 150. 5 into 30 is plus 150. Plus 150 is here. And then I do reverse. Then I go here. Right? This is 1. So this is VRY5. Okay. This is VRY5. The second one is 5 into minus 120 degree. Where is it? That is 5 into minus 90 degree. Plus 30 minus 120 is minus 90. So minus 90, 1, 2, 3, 4. It would have been here. It would have been here. It would have been here. But we negate it because there is a negative coefficient. So negative coefficient is this. So this would be VRY5, right? And the third one is plus 90 degree, plus 150 degree into 5, right? So 150 into 5 is how much? 150 is equal to 750 degree. 750 degree means 620 plus 30. So 620 plus 30 is here, then negate it. Therefore, it is coming here in this direction. It is coming in this direction. Coming in this direction. So therefore, this is the original. This is RY5. This is YB5, and this is VBR5. So that is where they are located. So what is that suggesting? That the phase sequence has now altered, because this RY is here, YB is 120 degree leading. Therefore, the phase sequence is now altered. The phase sequence is R not Y now, B and Y. So R5, B5, Y5 phase sequence will be getting in the case of the fifth harmonic. What about the seventh harmonic? What about the seventh harmonic? If I do the seventh harmonic, we'll see that this angle is now again we are doing the integration. Seventh harmonic case, we'll do the integration, and the coefficient will be still be minus √3/2. That coefficient will be √3/2. So we'll write VRY7 is equal to minus √3/2, 4 into VDC by 2, 4 into VDC by 2 by 7 pi. So that will be the thing. 4 into VDC by 2 into no, 2 twice I have done, and this √3 by 2 is included. So this into sine of 7 into omega t plus 30 degree, right? So VYB7 is equal to minus √3 by 2 4 VDC by 7 pi into sine of 7 into omega t plus 30 minus 120 degree, and BR7 is equal to minus √3 by 2 4 into VDC by 7 pi sine of 7 into omega t plus 30 minus plus 120 degree, right? So which if I do in a phase sequence way, so there will be, this will be now located, first one is what? First one is located at 7 into 30 is 210. So 210 in positive sense. So 210 in positive sense is this way. This is 0. Let us say it is 0. So 210 in positive sense is this way. So it is this, somewhat this. Then I reverse it. 210 positive sense if I do that, because it is minus √3 by 2. So it is here. Right? So this is VRY7, right? The other one is 7 into minus 90 degree. 7 into minus 90 degree. 490 degree, 7 into minus 90 degree is there, right? And then we reverse it. So where is that? This is this. So so this is VYB7, right? And the right. So 1, 2, 3, 4, 5, 6, 7, and then reverse it, right? The other one similarly would be located at this angle. At this angle. So this is BR7. Okay. So magnitude wise, whatever it was for a per phase multiplied by √3, this would have been for the per phase thing multiplied by √3. But interestingly, the phase sequence has altered for fifth harmonic, but not for the seventh harmonic. Seventh harmonic phase sequence is still RYB, because you see this is RY, this is 120 degree lagging, minus 120 degree lagging. So it is YB, and then that is another 120 degree lagging is VBR7. So this is what is the reversal of phase sequence is there only in the case of a fifth harmonic component. Right. It is very important to note this aspect of the thing. I will in a subsequent class I will tell you why it is so important to know. Okay, but quickly let us also do maybe you can complete it. Let us also see the what is the with respect to the motor neutral, what are the voltages, so that you can also do it for the motor neutral voltages. So if you do that, you do the integration. So here the step waveform is like this. Right, this is the waveform. And you remember the levels are VDC by 3, and this is 2 VDC by 3. So if we do the Fourier coefficient, again 2 by 2 pi, right? And this would be 4 into 4, and the integration is happening, fundamental integration is happening between 0 to 0 to pi by 3, 0 to pi by 3. This first one, the magnitude is 1/3. Okay, sine of sine theta d theta plus pi by 3 to pi by 2. We have broken it into 4 equal parts. This is the part 1, then next is part 2, and all are having the same integration value 1, 2, 3 and 4, 3 and 4, and that's why the term 4 is here. So this is we are doing only integration from between these two things, but here magnitude is 2/3. So 2/3 into sine of sine theta d theta. So this is the thing we are doing, and if we do it, we'll get it as 2 by 2 pi into 2 by 2 pi into this integration will be 1/3 into 0.5 plus 2/3 into 0.5, right? So into VDC has come out. VDC we should write it, VDC. So into VDC by into VDC by 2 into 4. So you see that VDC by 2 into VDC here, VDC by 3. So you will see that here it is magnitude wise again 2 by 2 pi into 4 into VDC by 2, right? So so this magnitude is exactly equal to 4 VDC by 2 pi, right? This is the same as the original one. Same as the original one means with respect to the neutral of the inverter terminal, the fundamental component of the voltage remains unchanged, right? So fundamental component remains unchanged. You will see that which is expected that the fundamental component is not changed because this is from one neutral to another neutral, and the difference between them only should be in the third harmonic component. So all other harmonic components should be identical. So there is no need to recalculate everything. Only we should check that the third harmonic component, this is what is, I will call it B1 of the waveform, or this is the waveform of VR R with respect to neutral N, VRN1. VRN1 is this one. So VRN1 is equal to 4 VDC by 2 pi into sine of omega t, right? So third harmonic component we'll see VRN, we'll see that component is 0. That component, if we integrate, we'll be finding out 0. But we will not see any change in, you can easily see that VRN5 is nothing but same type of structure. 4 VDC by 2 into 5 pi into sine omega t, and VRN7 is equal to 4 VDC by pi by 2 into 7 pi into sine 5 omega t here, sine 7 omega t, right? And the phase sequence will be maintained here, and there is no change in that, right? So we'll with this we just see that the phase sequence change, we have to see that in the next class how the phase sequence change produces a different kind of torque pulsations. The normal torque production happens between the flux and the current. So normal torque production, we'll see that the flux level of the machine, which wherever it is, and the current MMF of this machine, wherever it is, their angle between these two things, I am drawn a little wrongly, their angle will not be like that. The angle is somewhat like this. This is the flux, and this is the current. Now which flux and which current? Because the machine terminal voltage has harmonics. So which flux and which current? So therefore the torques are produced between fundamental voltage and fundamental current. Fundamental voltage and fundamental current. Torque also is produced between fundamental voltage and third harmonic current. And torque is also produced between third harmonic current, let us say, is not there. Fundamental voltage and fifth harmonic current. Torque is also produced between fundamental current and fifth harmonic voltage or fifth harmonic flux. Okay, so there is a combination of the things that are producing torque. So the total torque, if I want to write the total T total, I should consider this way. I should consider, I'm just writing combination wise, fundamental voltage and fundamental current. Current means MMF. You can think that MMF. I am writing to indicate that N is the number of turns. It is better to write it MMF and the angle between the two, and the angle between fundamental voltage and fundamental current, fundamental MMF. Okay, that is one combination. Plus, let us now change the fifth harmonic component. Fifth harmonic flux into fundamental current and the angle between fifth harmonic flux and fundamental current. Fifth harmonic flux and fundamental current. Similarly, if I just want to take the other one also, that there is a fundamental flux and the fifth harmonic current, and the angle between the fundamental flux and fifth harmonic current will also produce a torque. But these torques are not, has no average value, because they are angles. The fundamental has certain angle and fifth harmonic current has a certain angle, right? They are not in, because you have seen one is 5 omega t, another is omega t, right? So this angle is not constant. So therefore, the average value of them, do you know that two sinusoidal quantities, if they have two different frequencies, their average values are 0. Okay, so this instantaneously they have some value. Instantaneously they have some value, but they are not stationary. They have two different frequencies. So the angle between them is never constant. It is a function of time. So it is a function of time means on an average that thing will become 0. Okay, so that is what is called a pulsating torque. The fundamental voltage and fundamental current, both of them have got the same frequency, and the angle between them, which is normally known as the delta angle, and the torque is expressed as phi 1 into ni1 into sine delta. The delta 1, if I want to be very specific, the angle between the fundamental flux and the fundamental MMF, and their magnitudes are constant. When under steady state, their magnitudes are constant, and the angle between them, more importantly, their angle between them has reached steady state and there is a stable angle. So their value is constant. So that is what is the torque of the machine. We intend to have all the torque coming from that. But when you are not able to do that, when your supply system is a voltage itself has a harmonics, flux is also having harmonics. Why? Flux is nothing but integration of voltage, because always this relationship will hold good that V is equal to N d phi by dt. So flux is nothing but an integration of voltage. If the flux is there, voltage is 90 degree apart. This is the voltage. That is what we know, right? Because there is the differentiation and integration relationship holds there. So this is what is voltage, right? So this is what is voltage, this is what is flux lagging by 90 degree, and the relationship between flux and the current is producing torque. Okay, so this would be seen here that there is a stable torque and there is some pulsating torque. That is what is the problem of giving harmonics to the machine. You will have current, extra current, because of the harmonic currents. Why there is a harmonic current? Because even if we take the simplest possible equivalent circuit, if we take the simplest possible equivalent circuit, that this is the equivalent circuit of the machine and this is the leakage reactance combined together, just to get a simple, and this is the R2 dash by S, and this is JXM magnetizing current. And if you give a harmonic voltage here, you are giving V1, not only V1, you are giving V5, you are giving V7, etc., etc. So what is the change? Change is that this XM is there, but in this case XM, technically speaking, X5M, just 5 times, which is 5 times XM, and then X7M means 7 times XM, right? Here also X1 and then 5 times, comma, 5 times X1 plus X2 dash, and then 7 times X1 plus X2 dash. But whatever it is, there is some number here. There is some number here. So therefore, there will be a current here. There will be a current. There is no doubt about it, because V5 is not 0. It may be 1/5. V7 is 1/7 compared to V1. Compared to V5 is 1/5, and compared to this is 1/7. Magnitude is less. In fact, current is even less. Because why? Because this impedance is more, but still it is there. So it may be 1/5 and 1/5, not so much less, because R2 dash by S is not changing. So this impedance is decided by R2 dash S plus X1 plus X2 dash, JX1 plus X2 dash, the impedance that way. Only the reactive part is proportionally increasing, and but still there is some current. So it will be resulting into currents of I1, I5, I7 as well. I5, I1, I5, I7 as well, because this is the equivalent circuit from harmonics point of view. 5 times reactives, each one independently you find out and sum them up by superposition. That is the current, right? So, there is a stable current, and you must understand that these currents are not of the same frequency as I1. I1 is at a frequency of omega, I5 is at a frequency of 5 omega, I7 is at a frequency of 7 omega. Okay, but they exist. So I cannot combine this equivalent circuit into one form. I cannot write it in one expression. I have to independently come them together and find out each component of them. And if I want to find out the RMS, I have to probably square and add, right? So you understand that that is the fifth harmonic component is there. Similarly, there are fluxes. Fluxes will be phi 1. There will be fluxes of phi 5, and there will be fluxes of phi 7. Okay, what is the flux here? Flux here is just magnetizing current into this. The magnetizing current itself is less, but it is still there. Still there because they say there is a finite value of XM we are getting. So magnetizing current, fifth harmonic magnetizing current we will get, which will correspond to, which will produce V5 by 5 XM will be the fifth harmonic magnetizing current. Fifth harmonic magnetizing current, which corresponds to the flux. Similarly, here it will be V7 divided by 7 XM, which will corresponds to the seventh harmonic magnetizing current, right? And then they will interact crosswise. Fundamental current with fifth harmonic flux, fundamental current with seventh harmonic flux, and similarly seventh harmonic flux with fundamental current, fifth harmonic flux with fundamental current. And these torques, these cross element torques will be fluctuating in nature. This is what is called pulsating torque. Therefore, they produce pulsating torque. They produce pulsating torque in the machine because the frequencies are not constant. The variation is not constant. Therefore, their angle between them always is varying with respect to time. Okay, so I will stop here. Maybe in the next class I will give a diametric representation of this and clarify this point a little more. Okay, I will request you, those of you who are a little bit interested, to simulate one induction machine. May not be induction machine. You take RL load and take this inverter, develop the switching pulses like the way I have said, and see what is the current and what is the fifth harmonic component, what is the seventh harmonic component, etc., etc., and try to understand that whatever I am saying. You can take a simple RL load. Simple RL load you can take. Just RL load you can take, and you may put another inductor as a magnetizing inductor, and the magnetizing inductor value is very high. Take it per phase. You understand that this waveform, this circuit is a per phase circuit. So like that 3 phases you do it and see the waveforms and try to appreciate the things that I am talking about. Thank you very much.